Alrighty, nerds, we're going to go ahead and finish up the section, which is also going to finish out the chapter for us. And as long as everything goes to plan and we finish this today, nerds, then we will be able to have that extra day of practice tomorrow where we go over the skills that didn't go fantastically on the last test. So I think we got the day back. The math Lord giveth and he taketh away, but today he giveth it back. Okay? Yes, I did it. All right, so protecting an antenna. Realize that these word problems are not always going to be as plausible as the authors try to make them sound. Just kind of go with it, all right? They're doing their best to show you how the math can be used. A small satellite dish will be packaged with a cardboard cylinder inside it for protection. I don't know if you knew this, but if you look at a cylinder from the side, they look like rectangles. Anyway, this is going to be inside here to protect our dish. The parabolic dish is 24 inches in diameter and 6 inches deep. The diameter of the cardboard cylinder is 12 inches. What we want to know is how tall does the cylinder need to be so that it sits directly in the middle and is completely flush with the top of the dish. This way, if the box closed right here, it wouldn't crush towards the dish. Okay? So we need these to be exactly the same height, but we don't know the height of this. Parabolic means it's shaped like a parabola. So y equals x squared, kinda. Could be stretched or shrank. Speaking of, what does it mean to be parabolic? What would be really easy with this question was if we actually had an equation for this parabola. We don't. So we're gonna make one. So tell me, this vertex right here, where's an extremely convenient place for the vertex to be? At 0, 0. So what we're gonna do is we're gonna pretend it's at 0, 0. So this would then be our x-axis, and this would be our y-axis. So we put it at 0, 0. What do we know? We know that the dish has a diameter of 24 inches. We don't normally work with diameters, though. We normally work with radius, right? So then what's the radius? 12 inches, yeah. We have a radius of 12 inches on this dish. And I put it that far down from the x-axis for a reason. Oh, crap. I put the radius on the freaking box. I know. What am I doing? There you go. Radius of the dish is 12. Sorry. And I put it that far below the x-axis for a reason. It's because I want you to treat this as an x value of 12. And we already know the height. It says the dish is 6 inches deep. So that means from here to here is 6 inches. Well, that's a big deal. That's a big deal. Because what that means is if this is an x and this is its height, which is a y, I know the coordinates, quote unquote, of this point. That point has coordinates 12,6. And we're going to use that right now. Because we put the vertex at 0, 0, we know there's no vertical or horizontal translations. So there is no pluses or minuses anywhere. But what we don't know is if there was any type of stretching or shrinking. So what we'll do is we will allow for stretching and shrinking, because to be honest with you, if there was no stretching and shrinking, y equals x squared. If x was 12, y would be 144. It's clearly not. So there has been a shrink of some sort. So we'll write the equation as y equals unknown shrink value x squared. K is just a variable. We don't know what it is yet. We do know that it's a shrink value. It's going to make it so that our y value is 6 when our x value is 12. And by the way, I just clued you into how to do this now. Are you kidding me already? I can't catch a break. Anyway, yes?
I'm sorry, how do you know that it's shrunk?
Oh, so if it just says y equals x squared, well, you can't, let's get my fist out of the way. If it was the parent, y equals x squared, then if x was 12, then it would have been 12 squared, so the y value would have had to have been 144. So because the y value is so much less than 144, we know there's a significant shrink here, and we need to figure out what it is. And in fact, we're going to figure out what it is the way that I just told you. We're going to plug in this x and this y, and we'll solve for k. So we're going to replace our x with a 6, and, excuse me, our y with a 6, and our x, quantity squared, with a 12. Like I said, 12 squared is 144. And you're going to divide both sides by 144. You're not going to use a decimal, because decimals are not your friends. Because this fraction reduces very pretty. 1 over 24. Vertical shrink, factor 1/24. Adi. I just used it to stand in as a vertical stretch or shrink of some sort. Okay, so in mathematics, we often use K to be a constant. K for constant. I know you're like, but constant starts with a C. We go, yeah, but we use the letter C to mean other things in mathematics often. So a lot of times you'll see a K step in for constant. Also, you can't 100% quote me on this, but I believe the Greek word for constant starts with a kappa, which is a K, I think. I have Google, but I'm trying to teach. So, but anyway, so K is just some constant value that we had to figure out what it was. Constant meaning not changing. It'll be a number when we're done with it. So we have an equation for our parabolic dish, and that equation is y equals 1 over 24 x squared. And that is very useful information to us. That means if we knew an x on our parabolic dish, then we could use it to solve for a y on that parabolic dish. Oh, wait a minute. This box touches my parabolic dish right here. And this box has a diameter of 12 inches, a radius then of 6 inches. So from here to here is 6. Well, it's a box. So that means from here to here is also 6. This blue dot has x coordinate of 6. We don't know its y value yet, but we're about to find out by plugging it in right here. So we go y equals 1 over 24 times 6 squared, which is 36. So we have y equals 36 over 24, which, by the way, as a decimal, what? Yes, as a decimal, because it's a pretty one, is 1.5. That means right here, my parabolic dish is only at a height of 1.5. Let me break this down for you in another quick picture. Here was your parabolic dish. You found out that this value was 12. The top value up here was 6. Oh, and this number right here was 6 with a height of 1.5. Our job was to figure out how tall this box is. How do I get that number? Yeah, somebody whispered it. You just subtract, yeah. So the height of this box is 6 minus 1.5, or 4.5 inches. Please remember to use, what are these things called? Units, because it's AP. Please use your units so you don't lose a mark. So we took known information about our parabolic. We said it was at the origin, because life is good if it is. We plugged in the known information as an x comma y to solve for the number that must be in front of the x squared, because it's clearly been shrank down, because parabolas are usually pretty darn steep, you know. Then once we knew that, we took known information of the box, which does that, it had a radius of 6, figured out what the height of the parabola is at that endpoint, and know that this endpoint had a y value of 6. So once we knew this y value was 1.5, we were able to subtract. Pretty neat, right? Yeah. Okay. Then we'll move on unless you have questions for me. Yes, ma'am.
How would the height of the cylinder be 6 if the diameter?
Oh, no. The height of the cylinder is not 6. The height of the cylinder is this.
Oh, and we're trying to figure that out.
Mm-hmm. So we knew the parabola went all the way up to 6, which means the top of the box went all the way up to 6. And once we found out that the parabola was at 1.5 here, then we know that from here to here is just the difference between those two heights. The box had a radius of 6. because its diameter was 12. Cool? Awesome. I'm going to be real with you. This kind of question is easier to do with calculus than it is without calculus. We're going to do it without calculus because this isn't a calculus course. But that doesn't mean you can't do it. Here's what it says. Grain is leaking through a hole in the bottom of a storage bin at a constant rate of 8 cubic inches per minute. So notice it's units. Cubic inches, minutes. The grain lands on the ground and it's going to form a cone-shaped pile. You ever looked inside like an hourglass or something and noticed that when the stuff lands, it makes a cone? You ever notice that volcanoes are cone-shaped and things like that? That's because when matter flows in any direction but has to fall down, it will form a cone. That's just how it works, at least under gravity. Anyway, as this pile grows, the height of the cone always remains equal to its radius. So this will be equal to this. That's not always true. That's true to this question. If the cone is currently 1 foot tall, that's a different unit. How tall will it be in 1 hour? That's also a different unit. So the first thing we're going to want to do is let's make sure that we're working all in one kind of unit. This thing, the rate at which the volume of the cone is growing, is in cubic inches and minutes. I was told 1 foot tall. How tall is that in an appropriate unit? 12 inches. So this 1 foot is 12 inches. And I have a volume changing per minute. So I need to know this 1 hour. What is it in an appropriate volume or appropriate? 60 minutes is an appropriate unit. There we go. So now we're working in cubic inches, minutes. Life is good. We can start work from here. What we know is right now, this cone is 12 inches tall and 12 inches wide. Well, that's not true. It's 24 inches wide, but there's a radius of 12 inches because it says the height and the radius are equal. There are 2 different ways to approach this question. First way, figure out what the volume is right now using the volume formula, and then figure out how much the volume grew in an hour, or write an equation that doesn't have R and H in it, instead only has H in it, and then figure out what your new H will be after an hour, plug it in, yada, yada, yada. So there are 2 ways. I think the easiest way is to figure out what our volume is right now, figure out how much volume it will grow in this hour, add them, and then just solve for the new height. Let's do it that way. This is current volume. 1/3 pi r squared h. We're not going to type a pi button on our calculator. We're going to leave it as a pi symbol. And if you do 12 times 12 times 12 divided by 3, you will get 576. So this is 576 pi. That is our current volume. What we know is our volume, cubic inches. Sorry, yeah, I know, I would have lost a mark. That's our current volume. We know our volume is increasing by 8 cubic inches per minute for 60 minutes. So in 1 hour, we will have an additional 480 cubic inches. That is our new volume. Excuse me. That is how much our volume grew. My apologies. So new volume will just be whatever 576 pi is plus 480 cubic inches. That's our new volume. Now, let's write ourselves a volume formula where we can have this sitting in the place of v, and we can solve for the unknown height. So here we go. Volume is 576 pi plus 480 equals 1/3 pi r squared h. Oh, two variables. Oh, they're equal to each other. Oh, that's right. H equals r. And since h equals r, and we're trying to solve for h, because it says what's the new height, we want to keep h around. So instead what we do is we replace r right here with an h. So 576 pi plus 480 equals 1/3 pi h squared h, which is h cubed. And we now have the ability to PEMDAS in reverse order to get the h by itself. What's the first operation we're going to do to start getting this h alone? Well, it's not wrong, but it would be easier to multiply by 3. Yes, we're dividing by 1/3, but it's just easier to say times 3 on both sides. So I'm going to wrap both sides in parentheses, and I'll throw 3 on there. And when I do that, on the right side, these bad boys have canceled each other out. I'm not going to distribute this. I'm going to leave it alone. I'm going to run out of vertical space. That's okay. Trying to get h by itself. What's next? Divide by pi. I'm running out of space, so I'm going over here now. I have that 3 parentheses 576 pi plus 480 all divided by pi. No, those pi's don't cancel because there's a plus or minus stopping that from happening. Equals h to the third. Lastly, we just need to get rid of that third power with cube root or third root on both sides. Now, can you do this with a scientific calculator? Yes, but it would be a lot easier with our grapher, so I'm just going to get the answer with my graphing calculator. And we will round to 3 decimals because, well, that's what AP wants from us. On. I said on. There we go. It listened that time. I'm typing this as it sits in one go. That means I need to know where the cube root function is. If you press this math button right here underneath alpha, boink, and you look down to the 4th option, there's your cube root. Directly below it, the 5th option is any root you want. 5th root, 7th root, 12th root, the pieth root. Any root you want is number 5. But the cube root is here. So I'm just going to hit 4. Doink. There it is. This is a stacked fraction. Alpha, y equals, enter, stacked fraction. 3 print. Alpha y equals, it will bring up a shortcut menu, and it didn't on your calculator. That's because that's like the first generation. Okay, let's do it without the alpha y equals. It should still have a stacked fraction. Let me try. If you go to math, press the math button, go to the right to, no, excuse me, scroll all the way over to frac. Scroll, did she listen to me?
Yeah.
Is it there under frac? When you go over to frac, did it bring up an N over D option for you? Okay, I'm just going to pause the video. Anyway, now that we figured out that those calculators can't do it. Anyway, like I was saying, I have the ability to stack fractions, so I don't have to be a parentheses wizard. But if you don't have stack fraction on your calculator, you're going to have to be a parentheses wizard. Cool? All right. Anyway, 3 parentheses 576 second pi. Remember, pi is the second button and then the caret. plus 480, close your parentheses, all over, again, second pi, and you enter, and you're going to find out that the height of this cone hasn't changed much in the last hour. It hasn't even gone up a whole inch. It was 12 inches an hour ago, now it's 12.979 inches. Yes, 12.979 inches. What's that? You typed it in wrong. Hold on. Let me see your calculator. Okay. What is this garbage? Anyway, it's a Casio. Okay, so right here, you see where your cube root is?
Yeah.
Do you see the issue?
Oh, is it supposed to all be in a cube root?
It's all supposed to be in the cube root. So here's what you're going to do. You're going to say times pi. Where's your pi button?
It's shift, whatever the 10 in the bottom is.
Where's your shift button? Okay. Shift pi, enter. Are you kidding me right now? What is this garbage?
I don't know. I didn't want to pay $100 for a calculator. So
No, it's a good calculator. I'm just saying. I just don't know how to use it. So let's do this. Enter. Times. Why can't I? That number. Okay, here you go. Here's your calculator back.
Okay, thank you.
Figure out how to take that number, multiply it by pi, then, I don't know, or retype it all. There we go. 12.979. Let's say you're going to type it. Let me show you how to do it if you need to be a parentheses wizard. Math 4. Here's what it looks like for parentheses wizards. 3 parentheses, 576 second pi, plus 480, close parentheses, divided by second pi. And then you hit enter. Yes?
Oh, why, whenever you first got, in the very beginning, whenever you first got 576 pi plus 480, why didn't you just add them together right now?
Because I didn't want to have to write the decimal, especially because the decimal would have been rounded. So what would have happened was I would have had a rounded decimal here, and then I would have rounded again when I took the cube root. So when you're rounding a rounded answer, you've stacked errors on top of errors, and it makes your answers very wrong. What I did instead is called float. You want to float your answers, meaning, let me show you what else I could have done with it, can I? I'm trying to teach you guys things on the calculator. Please pay attention. Let me show you how to float your decimals on this calculator. Again, I don't know how to use that Casio. I'm sure it can do it. Cool, but I don't know how to do this. So if you want to know why I just didn't get a decimal for this, 576 pi plus 480 is. Okay, the calculator gave me a nasty decimal, right? Watch this. We know that that's what that is right there, correct? Times 3 is, divided by second pi is. You see how I didn't round ever? I'm letting the calculator handle it for me. And every time I type a new operation, it said, oh, your last answer. Oh, the last answer. And then I could do math 4 of, you ready for this? Right here above the negative symbol is ANS. Second ANS. Says cube root of the last answer. This is called floating your decimals. You could do that as well. But you don't want to round to 3 decimals early, and at the end, round again. Okay? Yes? Error carried forward, like follow through? Yeah. I would assume they do, but this is my first year as an AP teacher, and I have yet to ask this blue bomb, so I don't know. Let's go with they should, and if they don't, shame on them. Have follow through. Like if it's got parts A, B, C, D, and you goof up part A, but you do the rest of it correct. So what they should do, let's say you got part A wrong, but you needed that answer to do the rest of the question correct. They should only punish you in part A, but as long as you did everything right after that with that wrong first answer, you should get all the points afterwards. It's called follow through.
What if you put like the most simple answer for part A?
Okay, I don't know about AP, but I can tell you in IB, if you don't know how to do a part A, but you know you need it for part B, what you do is you make up a reasonable answer for part A, show no work, lose all the points for part A, but then use your reasonable answer in the rest of the question. And as long as you can do the rest of it correct, you still get the rest of the points. The point is you're being rewarded for showing off what you do know how to do instead of being multi-punished. Yes? Inches. because the volume of 8 cubic inches, you don't want to change that. If you're going to use feet, you'd have to go all the way back here and convert your 8 cubic inches to cubic feet per minute, which is remarkably small. Whatever the cube root of 8 is, the answer is 2 root 2, but it's a small number. We don't want to do that, okay? Oh, wait, no, it's even worse than that. It's like 9th root. I don't know. Moving on. Okay, this question is really neat. It doesn't require any graphing technology, and it's the first time you've ever seen something like this, but things like this will be used more and more and more starting in Chapter 2, but this is a great place to see it. Lou, who oversees ordering for a small retail outlet, tracks the total sales of each item in the store inventory at the end of each day. One particular fad item of clothing, it's really grabbed on, okay? And it's showing mounting sales over the first 10 days. What I'm seeing here is that every single day, I sold even more of these objects. Let's just say it's like the new pet rock or something like that, whatever. First day I sold 30, the next day I sold 56. That's not a 56 over 2 days. No. That's I sold 56 day 2. I sold 100 day 3, so on and so forth. And I'm hoping you can see that every single day we sold more than we did the day before. You see that? See it? Great. So although sales are going up, Lou believes that the sales curve will become logistic. And if you think back to section 1.3, the 12 basic curves, 12 basic functions, I should say, this is what a logistic curve looks like. It does something like this, where it goes up and then it starts to peter off and it has 2 horizontal asymptotes. One of them is the x-axis and the other one is up here somewhere. Anyway, Lou believes that these sales will follow a curve like that. And he believes that the time to stop ordering more of this object is when the inflection point is reached. Now, we talked about this once before earlier in the year. You probably don't remember what an inflection point is. An inflection point is the point where a graph changes concavity. So if you look to the left of somewhere in the middle of this graph, this is concave up. But if you look somewhere to the right of the middle of the graph, it's concave down, which means there is a point of inflection somewhere here-ish. At our level of knowledge, AP Pre-Calc, one of the ways we figure out where inflection points is we basically just find the middle between a maximum and a minimum of, the middle x value. But this logistic curve does not have a maximum x or a minimum x. That means there has to be another way of pulling that off. The question doesn't ask when does it happen. The question asks, how could Lou find the inflection point the day that it's reached using only this data? So what I did was I reprinted the data down here so I could write things underneath it. There will be times on your AP exam at the end of the year where it's not looking for an answer. It's looking for you to explain using math, logic, and rules how you could have found the answer. This is one of those questions. It involves a concept called first and second differences. We will do a lot of them in Chapter 2. For now, I'm going to show you how they work. Are you all familiar with the concept of slope? The rate of change. Well, it would be the change in the y's divided by the change in the x's, right? But look what the change in the x's is. It's 1s, which means my slope is literally the difference between 2 y values, because the difference in the x's is 1. I'd be dividing by 1 every time. So we are going to find the first difference, which is our slope, by subtracting the y values at each interval. Now, what do we know? We know that because the number of objects sold was higher every day than it was the day before, every one of these first differences, which represent slopes, are positive numbers. We know that because the number of objects being sold is growing. So we're literally just going to subtract the right one minus the left one, like we're doing a slope. Okay, 56 minus 30 is 26. 100 minus 56 is 44. 167 minus 100 is easy, 67. 250 minus 167 is 83. 333 minus 250 is 83 again. 400 minus 333 is 67. 445 minus 400 is 45. 470 minus 45 is 25. And on the last day, I only sold 15 more than the day before. What do you see? What do you notice about my slopes? The slopes seem to follow a parabolic curve, don't they? You don't have to write that. But look at the numbers. You can see that the slopes were increasing for a while, and then stopped increasing, and then started decreasing. So even though I had a positive rate of change at every day, the rate of change was also changing. So the rate of change was growing for a little while, stopped growing, and then started decreasing for a little while. And students who have taken physics before, when I say the rate of change of a rate of change, well, what's a rate of change we're all familiar with? Velocity is a rate of change, like the speed of your car. So if I say the rate of change of the rate of speed is changing, what am I describing? Acceleration. Acceleration is literally the rate of change of the rate of change. It's the slope of the slope. And because my x values are only increasing by 1 each time, the first difference was my rate of change. The second difference will be the rate of change of the rate of change. Time to find my second differences. And like I said, this is my second differences. And we literally just subtract again. I'll use blue. 44 minus 26, 18. 67 minus 44, 23. The rate of change of the rate of change is growing, look. 83 minus 16 is, did I subtract right here? This is 18, right? And this is 23, right? Okay, I was making sure. This is 16. Uh-oh, stopped growing. And then, 0. Now, the rate of change was still positive, but look at the rate of change of the rate of change. 67 minus 83 is negative 16. 45 minus 67 is negative 23, 4, 2? Help my math. Negative 22? Okay. Negative 20. Negative 10. Guess where the inflection point occurred? So this is the first difference because it's the first time I subtracted my y values? No, this is pink and this is orange. I'm sorry, it's hard to tell. Now that I've said they're pink and orange, it might be easier to see the difference between the two. In real life, on my paper, it's remarkably different. It's just what between the camera and the screen, it makes it tough to see. But it was these two pens. See? This is my red one. Anyway, guess where the inflection point was? Well, at which numbers? This one right here. At the end of day 5. The question didn't say when did it happen. Actually, yes, at the end of day 5. I said that right. No, at the end of day 6. Because look, this was the second 83. We saw the second 83 at the end of day 6. Which means by the end of day 6, we would have had this second difference of 0. And gone, inflection point. So when the second difference is 0, you have found an inflection point. As it turns out, and we're going to cover this a lot more next chapter, as it turns out, when your second differences are positive, your graph is concave up. You don't have to write this down. And when your second differences are negative, your graph is concave down. And we'll talk about that more in chapter 2. The question says, how can you find out when the second differences change sign, there is an inflection point. And that's true always. When the second differences change sign, you have an inflection point as long as you had a smooth, unbroken curve. Cool beans, huh? I think it's neat. Yes, sir.
So is he even asking for an answer?
No, it just said, how could he figure it out?
So if there's another question like this with data, you just write that same thing.
Basically. Now the question is, if you wanted to say when it happened right there at the end of day 6. If you wanted to say when. Because you couldn't get this difference, the second 83, until after day 6 ended. But then once you had your second 83, you could go, oh, my second difference was 0. Boom. And then don't order more inventory. Yes?
If there's like a,
Hold on. 2 questions. Hold on. Charlie?
if there's an answer box, would you write like find the first difference and the second difference? Or
No, you just say when the second difference changes sign, there is an inflection point.
you wouldn't even have to show your work if you just knew how to do it.
Right. But you've never seen this happen before. So how do we identify inflection points from data? That's how. Now, let's be real. A question would actually say, where is it and how did you know? So you would say, oh, it's going to happen on day 6 because that's when the second differences change sign. So you'd have to give an answer and a how you know. And that does happen in AP questions, excuse me. What's the answer and how did you know? You do have to justify in AP questions. Yes?
So it happens at the end of day 6 and not at the end of day 5 because 0 goes to positive numbers and you're splitting.
It's because 0 is not positive or negative. So this is where the change occurred. As far as you're concerned. To be honest with you, finding inflection points is something you do with calculus. You do it in Calc 1. It's remarkably easy to do once you know some stuff about Calc 1. But until we know calculus, this is the best way to do it. Yep.
Will it be on the test?
No, not yet. It'll be in the Chapter 2 test. But I need you to know about it now when I start talking about it for Chapter 2. But what is on the test is this next example, so we need to get to it. Because I need to get through this example before the bell rings. I only have 10 minutes. The table below records the low and high daily temperatures observed on September 9th, 1999 in 10 major American cities. That was my freshman year of high school, I think. 99, 2000, 2001, 2002, 2003. No. Yeah, that was freshman year of high school. Anyway, September 9th, 1999, 10 major American cities. Boom, boom, lows and highs. What we're going to do is find a function that approximates the high temperatures as y values as a function of the low values. We are then going to use that function to predict what the high temperature was for Madison, Wisconsin, given that the low temperature that day was 46. Now, because we haven't started Chapter 2 yet, we are going to assume, for now, that this is linear. Once we do Chapter 2 and we start talking more about first and second differences, we'll be able to identify just by using differences whether or not we're working with linear or quadratic or cubic, so on and so forth. For now, because we're in Chapter 1, we're going to assume linear. Cool? Straight line. Y equals mx plus b type stuff. And you have to use your graphing calculator to do this. So please pay attention to the commands on how this works. This is going to use the statistics functions of our calculator because this is a table of data. So come over here to stat, right there underneath delete, and hit stat. The very first option that's already highlighted says edit, and that's what you're doing. You're editing some lists. Now you'll see that my lists are already filled out because I did this in second period. But what if your lists are filled out and you need them cleared? Here's how you clear a list. You go up and highlight the list name. Don't press delete. You'll delete L1. No. What you want to do is clear it and then hit enter. Go over to L2, clear, enter. Someone said I already did. Did you delete your list? It means your L1's been deleted. Okay, bring it here. I'll show it on camera how to add it back. Quick, quick, quick. In case anybody else is missing theirs. So you're missing an L1. That means at some point in time you deleted it. This right here, where it says delete, its inverse operation is insert. So I'm highlighting L2, second insert, and now it wants me to name it. I'm going to name it L1, which is the blue answer right there, or the blue number. So second L1, I'll hit enter, and archived. Uh-oh, you have it archived. So I'm going to go to it. You've archived this thing. So let's go to second memory, and I'm going to unarchive L1. Done. Stat, edit, insert, second L1, enter. There you go. Your list is back. And if you wanted to be able to do any of that, you can always watch the video again. Okay? All right. Now, I'm going to fill my list out. I'm going to be very careful to type everything carefully and double check it as I go. X is L1, so 70, enter. 62, enter. So on and so forth. You can press enter to go to the next line down, or you can press down to go to the next line down. Whatever you want to do. I love the sound of button clicks all over the classroom. Sounds like nerd fun. I'm ahead of you guys, so I'm going to press right to go to my next list, and I'm going to do that. It's awful noise. Doesn't this class get out of it? Oh, I don't have enough time to finish. That sucks. Well, here's what's going to happen. You guys are going to leave, and I'm going to finish this video, so you're going to have to watch the video to see how it's finished. So I'll pause it until after you leave. Okay, now that everybody has left, my room is just so pleasant smelling and cooler because all of those warm brains that are thinking so hard have left. Jokes, of course, jokes. Anyway, guys, sorry that the last period didn't get to see how this finishes up, but these are the commands that you need in order to get a y equals mx plus b from an x comma y list. First, you press stat because, like I said, we're still doing statistics. And we're going to go over to calculate because we're asking the calculator to do some calculations with our current statistics. We're going to go down to option 4, linear regression, linreg. Look, it looks like y equals mx plus b. Mr. M, there's another linreg. What does it do? I have no freaking idea. So anyway, we're going to use number 4 only. So I'm just going to press 4. Boink. Now, it'll default to saying your x list is L1 and your y list is L2. And by default, you shouldn't have anything in your frequency list right here. If you have something in the frequency list, come down and delete it. And if these two are switched for some strange reason, remember you can delete it and you could, I'll just go ahead and show you what happens when it's cleared. I can come down here and I can do second L1 and it's there. Anywho's it. So we have X list is L1, Y list is L2. Come on down to calculate, highlight, press enter, and there it is. This is our Y equals MX plus B. And since it's AP, we're going to round to 3 decimals every single time, giving us, what's a good color? Purple's a good color. I've been writing a lot of purple. Let's use blue. Y equals a slope of 1.035x, which the interpretation of that is for every extra degree in low temperature, you're going to get a little bit more than 1 degree in high temperature, which is bad news for places like Phoenix. Eek. Ooh, it was warm there. Plus the B value, 19.254. Interpretation is 19.254 would be the high temperature if your place had a low temperature of 0. Anyway, we don't need this anymore. We have been asked, well, I'll use it for calculations. We've been asked to figure out what the high temperature is, a Y value, in Madison, Wisconsin, when we know the low value is 46. Well, that's an X value. So I'm going to put that right there. I don't know the Y value, though. So we're saying Y is 1.035, taking the X value we know, substituting it in, so parentheses, because good mathematicians. 46. And the only reason why I'm grabbing the calculator is because I'm not trying to do that multiplication right there. So let's see. Second quit takes us out to our main screen. 1.035 times 46 plus 19.254 is a very pleasant 66.864 degrees. 66.864 degrees. And I know you weren't here to hear it, and I know you really miss it. So thanks, nerds. It was awesome.